Hi guys, this is the EdExcel AS level further maths paper which covers the decision 1 section, and it's from the June 2018 series. Okay, so I think at this point it's a good idea to take a quick look at the examiner's report for this particular paper. Now, in terms of the overall comments, I've highlighted the important bits from the examiner's report, which of course you can take a look at. Now, this paper seemed accessible to most students. That's the first thing I noticed, which is pretty good. It's only the AS level, so I think this paper should be fairly straightforward to most people. One thing that was pretty clear to the examiners was that students should be reminded of the importance of displaying their method clearly. In a module like this, the reason that's important is because of this statement over here. This is a methods-based examination, so if you spot the correct answer but give no working, often that could lead to 0 marks essentially. So I would advise, particularly in this module, to make sure you show all your working. Now, the space provided in the answer book and also the number of marks allocated to each question should indicate to you the amount of work you need to do for the question. One other thing that is quite noticeable is that some people had very poor handwriting, and that is very difficult to read. So I would suggest working on your handwriting, or at least making sure that your working is reasonable. And I think the last point to make about this paper is that make sure you use technical language, even if it means revising mark scheme answers or textbook model answers. Make sure you go over certain definitions, particularly in a module like this. Question number 1. We have over here figure 1, which represents a network of roads, and the number on each arc represents the time taken in minutes to drive along the corresponding road. And for part A, we have to use Dijkstra's algorithm to find the shortest time needed to travel from A to H, and then we have to state the quickest route. So if we take a look at this figure, we've got essentially this top box on the left, which is the vertex, the middle box, which is the order of labeling, this box, which is the final value, and then we've got working values in the bigger box at the bottom. So if we're starting at A, we want to end up at H. Of course, starting at A to B, so far that's 3. A to D, that's 25. And then A to I, that's 12. The smallest one so far, you'd find that to be 3. So therefore, in the order of labeling, B goes second. And the value we take forward is this 3 over here. We now look at the smallest ones remaining. Now that we've done that, B to C, 3 plus 5, that's 8. We look at the smallest ones between 8, 25 and 12. You'd find the smallest one to be 8, and therefore 3 belongs to C, and we take in this number 8. Okay, now from C to D, 8 plus 14, you'd find that to be 22. CTE 8 plus 6, that's 14. And that's all we can complete for now. We then look for the smallest one between 14, 25, 22 and 12. 12 is the smallest one, so we carry the 12 into this box and then we give I the label 4. Now, from I, 12 plus 7, that's 19. 12 plus 10, that's 22. And looking at everything else, that's all we can fill in. So the smallest ones between all of these, you'd find that to be the 14. So the 14 goes here, and then we label I with 5, and then we continue. 14 plus 7, that's 21. 14 plus 8, that's 22. 14 plus 16, that's 30. And that's all we can fill in for now. And therefore the smallest one over here would be this 19. So the 19 we take into this box and we label F with the number 6. Okay? Now, from F, 19 plus 9, you'd find that to be 28. And that's all we can fill in for now. And out of all of these numbers, you'd find 21 to be the smallest. So we take 21 here and we label D with the number 7. Okay? Now, with these remaining boxes, we then look for the next smallest one, which is this 22 over here. So we take this 22 in here and we label that with the number 8 for J. Okay? Now, 22 plus 23, you'd find that to be 45. Okay? So we put 45 here, and we look for the smallest ones out of all of these. You'd find that to be this 28. So we put 28 over here, and then that this G, that corresponds to number 9. So we've done all these so far. And then, of course, 28 plus 11, you'd find that to be 39. So we put 39 into the working box, and therefore the smallest one now out of the one that's left, which is this one, that's 39. And therefore H corresponds to 10. Of course, with box A, we started at 0, so we have 1 over here, and we took this 0 here. Okay? So, in terms of the shortest time, you'd find that to be this value of 39. So the shortest time is 39. And the quickest route, we'll have to work the route, and to do this we'd have to work backwards. So 39 take away 11, that was 28. And then from here, 28 take away 9, that was 19. So we went back here. And then 19 take away 7, that was 12. And then here we go back to A. So the quickest route, we have A, I, F, G, H. Okay, so that was the quickest route. And now for part B, for a network with n vertices, Dijkstra's algorithm has order n squared, and if it takes 1.5 seconds to run the algorithm when n equals 250, we have to calculate approximately how long it would take to run the algorithm when n equals 9500. You should make your method and working clear. So we're looking for the time. Now our scale factor is 9500 divided by 250. And then because Dijkstra's algorithm has order n squared, okay, so because Dijkstra's algorithm has order n squared, we must square this scale factor. And then our original time, we know that to be 1.5 seconds, so therefore we multiply this by 1.5, and therefore, working this out, we get 2166 seconds. I suggest writing down your units too. For part C, we have to explain why your answer to part B is only an approximation. We have the following reason. So the order of n squared does not mean that the order is proportional to n squared. That was the assumption that we made in part B, but rather it means that the dominant term is of order n squared. So there's a slight distinction there. In terms of question 1, this was probably the most successful part of the entire paper. Most people answered it very well. There were common errors, you can have a read through them, but I think if you take everything step by step and do everything slowly, much like I did, I think not missing steps is very difficult to do in that situation. There was also some bit written about the shortest time and the quickest route. State those in. Often under pressure you might miss little things like that out, so make sure you do include things like that in. Part B was pretty well done. Some of the errors over here was that students were confused and treated this as a linear relationship rather than a quadratic. I mean, we're told in the question somewhere that we have something of order n squared. And other errors included incorrectly squaring the constant of proportionality. And that's the 1.5 over here. You square this sort of scale factor. Part C was something a bit more challenging. What's important over here, what stands out to me is that some students were confused by the meaning of run in the context of algorithms and talked about getting tired when running longer distances, and very few gave textbook explanations. Okay, so I think when it comes to questions, you have to refer to the lack of exact direct proportionality between runtime and n squared. Okay, so I think again giving textbook answers would help in this situation. Question 2. A simply connected graph is a connected graph in which any two vertices are directly connected by at most one arc and no vertex is directly connected to itself. That's a fairly standard definition which I recommend you all learn. Okay? Now, for part A, given that a simply connected graph has exactly 4 vertices, we have to write down the minimum and maximum number of arcs it can have. So I've got this quick diagram. We've got 4 vertices, and the minimum number, we can draw a quick simple connected graph like so, and you'll see the minimum number of arcs here is 3, and the maximum, well, we can connect this to this, we can connect these together. Okay, so we can connect these together, and then these together, and then we can connect these corner ones together. We can connect this with this, and therefore what you'd see over here is we have 1, 2, 3, 4, 5, 6. So therefore the minimum number of arcs is 3, the maximum is 6. Now for part B, for the first part we have to draw a simply connected graph that has exactly 4 vertices and exactly 5 arcs, and then state with justification whether your graph is Eulerian, semi-Eulerian, or neither. So we want over here to have 4 vertices but 5 arcs, and we want the graph to be simply connected. So we can connect this to this, this to this, and then this to this, and then this to this. We want the graph to be simply connected but with 5 arcs, and therefore we've got 4 arcs so far. This is all simply connected, and if I join one of the corner ones to the other corner one, you'd find over here we have 4 vertices and 5 arcs, and therefore for the next part you'd find over here that we have exactly 2 odd nodes. Let's just show these. We have this which has 3, this which has 3, this which has 2, this which has 2. Over here, of course, I'm referring to the order. So we have exactly 2 odd nodes of degree 3. Okay, and therefore we have something which is semi-Eulerian. Okay, now part C, that's a bit more tricky. By considering the orders of the vertices, we have to explain why there is only one simply connected graph with exactly 4 vertices and exactly 5 arcs. Well, here we have to use the handshaking lemma, and I'll just write the definition of that down. So the handshaking lemma, the sum of all the orders of vertices of any graph is twice the number of arcs. Now if you go back to the question, we were told that we have exactly 5 arcs and we have 4 vertices. So therefore the sum of the orders of the vertices, we have 2 times by 5, where of course 5 is the number of arcs. So we want the sum of the orders of all the vertices to be 10. Now, we were also told in the question that the graph is simply connected, and by definition a simple connected graph cannot have a vertex with order 0. Let's just write that down. So a simple connected graph cannot have a vertex with order 0, and if we go back to the definition of a simple connected, essentially any two vertices are directly connected at most, by at most one arc, and no vertex is directly connected to itself. So that's why we can't have this order of 0, which I'll also highlight in this colour as well. And remember, we want the sum of the vertices to be 10. Okay? Now, if we have 4 vertices, okay, then the maximum order of a vertex is 3, but the minimum order of the vertex would be 1. Okay, let's just write that down. So the maximum order of a vertex is 3 and the minimum order is 1, and of course this is true for a simple connected. Okay, now remember, we have 4 vertices. Okay, so we have 4 vertices, and we want the total order of these 4 vertices to equal 10. Now, one combination we can try is, if we write this down, a possible combination we can try is 3 plus 3 plus 3 plus 1. Okay, but you'd find this to be impossible, and the reason it's impossible, if I draw 4 vertices and connect them all, we want 3 of them to have order 3 and 1 of them to have order 1. Well, here this one has order 3, then we can connect this, and then this has order 3, but then this has order 2, and if you want another 3 over here, then this would have to change to a 3. So essentially, for a simple connected graph, this situation is impossible. Okay, so this is impossible. And the reason it's impossible is that this is impossible for simple connected. Okay, and the reason it's impossible is because each of the vertices of order 3 must connect to 3 other vertices. Okay, so each of the vertices of order 3 must connect to 3 other vertices, so the other vertex cannot have order 1. Okay, now again, remember, we want the simply connected graph to have an order of 10. So one other possibility we can have is 3 plus 3 plus 2 plus 2, which is what I tried to draw out before. So let's just write that down. Another possibility of combination is 3 plus 3 plus 2 plus 2. Okay, and the reason this works is essentially this over here ensures that the 2 vertices of order 2, which are these two, and the two vertices of order 3, which are these two, are all connected to each other. Let's just write that down. So we've got over here the other possibility, which was 3, 3, 2, 2, and this ensures that the two vertices of order 2 and the two vertices of order 3 are all connected to each other. Now, I think it would be a good idea right now if we draw out all the different possible combinations that we could have. So the first case, we could have this situation over here for simple connected, and then, well, we'll draw them all out first. Actually, no, we'll do it this way. You'd see that here we have order 1, 2, 2, 1. The other possibility we could have is this situation over here. So we could have this connected to this, and then this connecting to this, and then here you'd see we have 1, 3, 1, 1. The other possibility is this situation, where you'd find we have orders of 2, 2, 2, 2. Another possibility, we can have this situation where we have this connected to this connected to this connected to this, and then this connected to this, and you'd see that the orders we have 1, 2, 3, 2. The other possibility we can have is this situation where these are connected, and then this one diagonal is connected, and you'd see we have order 2, 3, 2, 3, and then finally we can have this and this connected, this and this connected, and then both the diagonals connected, like so. And then you'd find we have 3, 3, 3, 3. Okay, and you'd find then here we have a total order of 1, 2, 3, 4, 5, 6. Here we have a total order of 1, 2, 3, 4, 5, 6. Here we have 8, and for these bottom three we have 8, 10 and 12. And remember, we want 5 vertices, we want a total order of 10 with 4 vertices. So this situation is the only situation we can have. Okay, so let's just box this off. This over here is the only possibility we can have. Okay, in terms of question 2, that talks about graph theory. Many students struggled with this question. Part A was pretty much well done, but some common errors were to write 4 and 6 for the minimum and maximum instead of 3 and 6. Now in terms of part B, I think if you draw the graph correctly, then you can figure out whether it was semi-Eulerian or Eulerian or neither. And if you found it to be semi-Eulerian, you have to give exact definitions in that, stating that if it's semi-Eulerian, the graph contains exactly 2 nodes. Now to part C, in terms of part C, that was a bit more difficult mission. A lot of people, first of all, found this to be pretty challenging. Many did state that the sum of all the vertices should be 10, which is good. But I think the problem was over here was that they did not consider what would happen if you have an order of 3, and they failed to sort of explain that further, and that's exactly what I did over here. I explained it further. So what you have to do over here then is develop that argument into a discussion. There was also the problem of people writing more than what was needed, and I think handwriting gave a bit of a problem as well in terms of answering this question and getting the correct answer. So graph theory, I recommend, if it's something you're struggling with, I recommend looking at other exam boards and checking out their questions on graph theory, particularly those from the older spec. Question 3. We've got this table over here which shows the activities required for the completion of a building project. For each activity, the table shows the time it takes in days, and the immediately preceding activities, each activity requires 1 worker. The project is to be completed in the shortest possible time. Figure 2 shows a partially completed activity network used to model the project. The activities are represented by the arcs, and the number in brackets on each arc is the time taken in days to complete the corresponding activity. And we have to add in the missing activities and necessary dummies to diagram 1 in the answer book. Well, before that, I think it's always a good idea to sketch what you want. So we've got this over here. Maybe if I shrink this slightly, you can see over here, I don't know how clear this will be on the screen, but we've got our source over here, okay, and coming out of that we've got A, B and C. They don't depend on anything. So we have A, we have B, and then we have C. Okay, and that takes us to these 3 points over here, and then we have B, which is connected to F. And does this make sense according to this? Well, if you look at F, B precedes it, so yeah, that does make sense. So once B is completed, we can start activity F. Okay, so here we have F, and perhaps if we make this slightly bigger, so that's the completion of A, and then here we have the completion of C. Now if we also take a look, well, I think it would be a good idea now to tick off what we've completed. We've completed A, we've completed B, we've completed C, we've not yet completed F. F has more activities, and hopefully you can recognize that this C and this C and this H and this H indicate to us that we need dummies. Okay, so let's look at D. D depends on A. And what depends on D? In terms of what depends on D, H depends on D as well. So, and if we take a look at H, H also depends on F to be completed. So if we say that F is completed, D depends on A and H depends on D. So if we say H starts from here, so let's go across here to H. Obviously that's in line with what we have over here. We have D, which needs to be completed before we start H, and D depends on the completion of A. So let's connect these two together. So this over here would be D. Okay, so in terms of what we've done then, we have over here A, B, C, D. Is F completed? Yeah. If we take a look at F, F depends on B, and F also depends on F depends on E. And if we take a look at E, E depends on A. So for F to start, we need to finish E before that, and E depends after the completion of A. So E can go over here. So this is E. Okay. Now that's F. F depends on B, C, and E. Well, we've shown that it depends on B and E. We need to somehow show that it depends on C as well. And if we take a look at G, G depends on C. So G can start when C finishes. And if we take a look at G, G depends on C, and in terms of what depends on G, H depends on G to be completed, and G depends on C to be completed. So we can connect these two together. So here we have G. Okay, so this is activity G done. So after H we have I and J, right? If we take a look at I, let's just draw a line over here. We have I completed over here, and also J depends on H. Now we can't have essentially some sort of a loop like this. We can't have this situation going on, because that contradicts the rules for dummies, in that we can have at most only one activity between two events. So instead, if we get rid of these, if we have H over, if we have J over here, then we can have a dummy in between these two, like so. Okay. So you'd find that to complete I and J. Okay. So that's I and J. Now if we take a look at H, H depends on D, it depends on F, and it depends on G. So that's done. And the only one we've got left is over here F. F depends on B, C, and E. And for the exact same reason, we have a dummy over here between C and, well, if we think about F, F requires C to be completed, so we would have to have a dummy over here, because again, one of the rules is that we can have at most only one activity between two events. So this over here is our completed diagram, and perhaps let's just write that down. We need a dummy, so dummy required when we have at most only one activity between two events. Okay, so that is the justification for us having a dummy, which we showed here and also here. Okay, so what you'd find over here, I've just completed this over here, and now we just need to fill in the letters and the numbers. Let's start off with the letters. Here we have E. So we have E over here, D here, F is already shown, we have G over here, and we have J over here. I think that's it. and we now need to add in the numbers. So if we add in the numbers, we have G, which is, if we go back here, G is 7. We have D and E. D and E, that's 14 and 10. So we have D, which is 14, E, which is 10, and then we have J, which is 9. Okay, so J is 9. Okay, let's perhaps if we rub this out, we have J, which is 9. Okay, so that's everything completed. And just as a reminder, we require dummies here and here, because at most only one activity between two events is necessary. Okay, so that is pretty much the end of that. And now we have to, for part B, complete diagram 1 in the answer book to show the early event times and the late event times. Okay, so what we're doing over here then is both part A and part B. Now, of course, we start off with the early start time, so we have 0 over here. And then 0 plus 5, that's just 5. 0 plus 4, that's 4. And then, well, you have to be a bit careful here. We can either have 5 plus 10, which is 15, or we can have 0 plus 8, which is 8. We choose the bigger, we choose 15. Okay? So hopefully you should all be familiar with why I did that. And then obviously here we have 0. Now, if we consider this box over here, we have 4 plus 7, which is 11. We have 15 plus 3, which is 18. And then we have 5 plus 14, which is 19. The biggest one is 19. We want 19 to go inside here. Okay? And then 19 plus 5, that's 24. 24 plus 7, well, we have got to be a bit careful here. Of course, here we have 0. 24 plus 9, we have to do J first because this depends on this over here. So 24 plus 9, that's 33. And then 33 plus 0, that's 33. So we have 33. Or we could have 24 plus 7, which is 31. We choose the bigger one. So we want 33. Okay? And if we work out the late event times, we want 33 over here. Now, 33 take away 0, that's 33. Now here we can either have 33 take away 7, which is, if I work that out, 33 take away 7, that's 26. Or we could have 33 take away 9, which is 24. We want the smaller one, so we choose the 24. Okay, so hopefully that makes sense so far. And then working backwards again, well, 24 take away 5, that's just 19. Now what else do we have? Well, 19 take away 14, that's 5. And then we have 19 take away 7, that's 12. And if we work backwards over here, 19 take away 3, that would be 16. 16 is the only one that can go in here. Now 16 take away 0, that's 16. So out of the 12 and the 16, we choose the smaller one, which is 16. Sorry, which is 12. Okay? So hopefully that makes sense so far. And then 12 take away 4, that's 8. What else do we have? We have well, 16 take away 10, that'll be 6. We want the small one, so we choose 5 here. And then we have 0 over here, presumably, because we have 5 take away 5, which is 0. Okay, so where did this 8 come from again? 16 take away 8, and then we're comparing that with the 12 take away 4, which is 8, and then we have 5 take away 5, which is 0. Okay, so we choose the 0, which is the smallest one. I'm going to leave this 8 up for a second because we might need it in a later part of the question. But in terms of the critical activities, we have A, then we have D, and then we have H, and then we have J. Okay, those are the critical activities. And then we have 2 finishes. Okay, so now for part C, state the critical activities. Critical activities, we've just mentioned those. We have A, D, H, and J. Now for part D, at the beginning of the project, it is decided that G is no longer required, and we have to explain what effect, if any, this will have on the shortest completion time of the project if activity G is no longer required. Okay, so well, first of all, G isn't critical, so if it's not required, it doesn't really make a difference to the project. Let's just write that down. So for the next part, the reason for that was because G is not critical, so no effect. And then for the next part, we have to explain the effect on the time remaining of the remaining activities. Well, if you look over here, if G isn't needed, of course that directly affects C. And in terms of C, you'll notice over here, in terms of the early event time, we can start 4 days later then, okay, because we need to get this done by 16, okay, or alternatively we can start at 12. It takes 4 to complete, and of course here we'd have a dummy if G is no longer required, because we can't have C going straight to here. So we can start late at time 12. So that's the reason we've got over here. In terms of question 3, many people struggled with the concept of dummies. Remember, I talked about when to use the dummies, when you've got sort of, like in this example, a C for activity G and a C for activity F. In that case, you'd have to use a dummy. Same thing with I and J, you'd have to use a dummy there. So I think looking at what the definition of a dummy is would actually help. There were extra dummies involved, which was a problem. There were missing dummies as well between the nodes. There were dummies with missing arrows. That was a problem. There were some with no arrows whatsoever. And some activities were missing, so do be careful over here. I think what I did before when I was going through how to draw the full thing was I often ticked off the activities that I've just drawn on, and that ensured that I did not miss out any activity. The diagrams, I think the run about this diagram was often unclear. For those who drew a nice diagram, they were able to and it was quite a straightforward question, and if they were able to do that, they could write down the critical activities very easily. Okay, and part D, that was a bit challenging. You just had to sort of think about everything in context of this question. Question number 4. The manager of a factory is planning the production schedule for the next 3 weeks for a range of cabinets. The following constraints apply to the production schedule. The total number of cabinets produced in week 3 cannot be fewer than the total number produced in weeks 1 and 2. At most, twice as many cabinets must be produced in week 3 as in week 2. The total number of cabinets produced in week 2 and 3 must in total be at most 125. The production cost for each cabinet produced in weeks 1, 2 and 3 is 250, 275 and 200 respectively. The factory manager decides to formulate a linear programming problem to find the production schedule that minimizes the total cost of production. The objective is to minimize 250x plus 275y plus 200z, and for part A we have to explain what the variables x, y and z represent. That's quite a straightforward answer, in that x is the number of cabinets produced in week 1, z is the number of cabinets produced in week 2. Y is the number of cabinets produced in week 2, and z is the number of cabinets produced in week 3. And now for part B, we have to write down the constraints of the linear programming problem in terms of x, y and z. Well, from the first statement over here, we've got the total number of cabinets produced in week 3 cannot be fewer than the total produced in weeks 1 and 2. So if x is week 1, y is week 2 and z is week 3, using that statement we have x plus y is less than or equal to z. Okay, so that corresponds to the first statement. For the next statement, we were told that at most twice as many cabinets must be produced in weeks 3 as in week 2. So that tells us that z is less than or equal to 2y. And the last thing that we were told is that the number of cabinets produced in weeks 2 and 3 must be in total at most 125. So weeks 2 and 3, so that's y and z. So we have y plus z is less than or equal to 125. Okay, so that's the third statement. And of course we've got our fourth inequality. X, y and z must all be greater or equal to 0. Hopefully that makes sense. So that's part B done. Now for part C. Due to the demand, exactly 150 cabinets must be produced during these 3 weeks. This reduces the constraints to the following, which are shown in diagram 1 in the answer book. And given that the manager does not want any cabinets left unfinished at the end of a week, we have to use a graphical approach to solve the linear programming problem and hence determine the production schedule which minimizes the cost of production. You should make your method and working clear, and then we have to find the minimum total cost of the production schedule. Well, from this statement over here, exactly 150 cabinets must be produced in these 3 weeks. Now we've got our objective function. We'll call that equation 1. Let's just write that down here somewhere. We've got P equals x plus y, P equals 250x plus 275y plus 200z. Okay, and that's that over here is the objective function. Let's just write that down. This is the objective function, and we'll call that equation 1. And we were also told from here that exactly 150 cabinets must be produced during these 3 weeks. So what does that mean? If I just highlight that, that means that x plus y plus z is equal to 150. So we have x plus y plus z equals 150. Okay, let's just highlight that. And we'll call this equation 2. And if we rearrange 2, from equation 2, we have z equals 150 minus x minus y. We'll call this equation 3. And then we will substitute in equation 3 into equation 1. So we will substitute equation 3 into equation 1. The reason we want to do that is because if you look at this graph, that's in terms of x and y only. So we have p equals 250 x plus 275 y plus 200 z. Z over here is 150 minus x minus y. So we have p equals 250x plus 275y plus 30,000 minus 200x minus 200y. And if we simplify all that, you'd find p to equal 50x plus 75y plus 30,000. So we wish to minimize p subject to these constraints over here. Okay, and there's a couple of ways you can do this. I will only show the way I'm most comfortable with, and that is to use the coordinates of the intersection points. So we've got 3 intersection points, here, here and here. This intersection point is 2550. This intersection point over here is 37.5, and this intersection point here is, let's get a better colour. This intersection point over here is 25 and 41.25. Okay, hopefully that's all clear. And we can substitute these 3 points back into our function for p. So if we first of all consider this point over here, the 25 and the 41.25. First of all, we know that p is equal to 50x plus 75y plus 30,000. And if we consider that point of 25 and 41.25, if we consider this point, as soon as I find my ruler, we simply substitute all this back into our p over here. So we have p equals 50 times by the 25. Okay, and then we have 75 lots of this y value of 41.25. Okay, and then we have this 30,000 as well. So therefore you'd find p to equal, if we substitute all this into a calculator, we end up with 343.75. Let's now substitute in the other point, the 25 and the 50. So if we substitute in 25 and 50, we have p equals 50 lots of 25 plus 75 lots of 50. And then we have 30,000 as well. And if we work this out, you'd find P to equal 35,000. And if we substitute in this over here, the 37.5, so substituting that in, 37.5 and 37.5. If we substitute these into our P over here, you'd find P to equal 50 lots of this plus 75 lots of this plus 30,000. So let's just write that in, 37.5. You'd find P to equal 34,687.5. Now of course we want to minimize the cost, and you'd find the minimum cost is this one over here. So the minimum cost, you'd find that to be this value over here, and therefore this min cost of 34,343.75, this occurs when x equals 25 and y equals 41.25. Okay, so that's the minimum cost in terms of x and y. But remember, in this question, if you go back, in terms of the whole production schedule, we would have to use this equation number 2 over here. So equation 2, so if we now use equation 2, so let's write that down. So using equation 2, which, just as a reminder, z equals 150 minus x minus y, using these x and y values, well, actually, it's better, think of it as a better way to explain it. Remember, cabinets must be whole numbers. You can't have a fraction of, you can't have a sort of a fraction of a number. So therefore the integer values are 25, and this 41.25 we round up. So we have the integer values of x equals 25 and y equals 42, and then from this it would follow that z equals 150 minus 25 minus 42, which is 83. Okay, and therefore from this we can find out the production schedule. So the production schedule is 25 in week 1, 42 in week 2, and 83 in week 3. And in terms of the minimum cost, the minimum cost, therefore, well, if we use our p function which we had before in terms of x, y and z, we have p which is equal to, well, rather we have the minimum cost of p, which is 250 times by x. So we have 250 times by 25 plus 275 lots of y plus 200z. So we have 200 lots of 83. And if we work this value out, you'd find we have 34400. So that's the second part of part C, and that was the first part. Okay, and I think it would help if perhaps if we rewrite this as the if we write this instead as that the minimum occurs when, and if we rub this bit on, so the minimum occurs when x is 25 and y is 41.25, and then we found that the total minimum was this amount over here. Okay, so that's essentially it. Question 4 was quite challenging. It was a linear programming question. One problem was that students did not define variables correctly. Like over here, look at my definition, everything I defined was very clear in my opinion. So you had to be specific in how you define certain variables. For part B, inequalities were not always stated. Sometimes the direction of the inequality people got wrong. In terms of part C, we have a 3-variable objective function, but many people fail to convert that into a 2-variable objective function. And the reason we want to convert it into a 2-variable function is because we've got a graph in terms of x and y. And the way to do that is just to do a bit of rearranging. Some students did not state the objective function at all, which is very surprising apparently. And the remaining part of the question, there were 2 ways to do it. The first way was the objective line method, which I did not do. So that was just basically drawing the objective line and using the ruler test. Those who did this, they seem to have problems with their gradients. That's why I tend to not use that method. For the testing method, which is the method I used over here where we use the coordinates, you have to be a bit careful over here. First of all, those who use testing took a long time. I think it's better to take a long time provided that you answer it in the time allocated, to make sure you get everything right first. So one of the problems was over here was that the integer, they took long to calculate the coordinates of their vertices and then rounded to integer values before evaluating the objective function. So what I did over here, I worked out values before I did not do any rounding in these couple of steps over here. Some students worked with the exact coordinates, so there were a few who used the objective function, which was the p function over here. There was also premature rounding. Be careful with your rounding. In terms of what else was said, so in terms of the next part of the question, you had to reintroduce the z variable, and many students forgot to introduce that z variable. So I think overall, I think the paper seemed to be very straightforward in my opinion. I think probably the more difficult question was the graph theory one. But yeah, anyway, I do hope this video helped. Don't forget to like, share and subscribe. And please do check out the playlist for more D1 videos.